Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. In this video, I will finish chapter 1 by explaining a few of the steps in section 1.3 on the restricted partition function, and then make some comments on the Frobenius coin exchange problem. So here's a bit of a guide through our computations in section 1.3. So we start with a restricted partition function p sub ab of n. So I think of a and b as given positive integers. In a moment we will also assume that they're relatively prime. They have no common factor. And n is a parameter. So I think of this partition function as a function of n. And as we talked about in previous videos, we write n as a linear combination of a and b with non-negative integer coefficients. And we think of this as partitioning n with parts that can only be a or b. From this partition function, we form the generating function. And this is sort of from first principle, so you can see here in my exponents, you can see the linear combinations of a and b. And so this generating function is the rational function 1 over 1 minus z to the a times 1 minus z to the b. So to extract the partition function, what I do is I take an extra factor of z to the n. So in this function, I think of n as another fixed parameter. And so the real function we want to study is this function that we call f of z. And my goal is to compute the constant term of this function. Because the constant term, so constant term means that this exponent is 0. And so the constant term is precisely what I'm looking for. It's precisely this partition function evaluated at n. Okay, and so as we discussed in the previous video, we'll do partial fraction expansion. And again, the point is that to compute this constant term, I can now compute the constant terms of each term down here. And we talked about this already a little bit. This really means I can neglect this first part, and after computing these coefficients in the partial fraction decomposition, b1, b2, the ck's and the dj's, and you're doing some of this in the exercises. So now I'm actually computing the constant term, and as we said above, what this gives now is an actual formula for this restricted partition function. By the way, it's in this partial fraction decomposition that I really need this condition that a and b are relatively prime. This means that the non-trivial eighth roots of unity and the non-trivial bth roots of unity are simple poles of f. Okay, so let's continue. So the first line here is just the previous line. What we then do is we look at a special case. This is a special case when b is equal to 1. And there's two reasons to look at this special case. So the first reason is from first principle, this restricted partition functions when b is equal to 1 has a simple form. This is a simple form in terms of the floor function. And what happens in my formula that we derived on the previous page is when b is 1, this second term over here disappears. And of course, I have a b in the exponent here, and and that's why you don't see it in the second line. And then we do a computation with this finite sum over here. So to handle this sum, we do just a little bit of number theory. So you see this in the third line over here. And so again, I'm using the fact that A and B are relatively prime. And what that means is I can do a change of variables in my summation according to the roots of unity that appear. Namely, if you think of these roots of unity and their counterparts over here, then I claim as a set, I'm going over the same set. And so what I'm doing is I'm re-indexing the parameter k by multiplying it by b. And you can also think about the other side. So if I have a simple k over here, that means on this side I need to multiply by b inverse. This allows you now to use the formula that we have up here, which really says that this sum can be expressed as a simple form in terms of the floor function and some easy rational expression. And after all of this is said and done, what you get is this theorem down here, where we have a nice sort of closed and easy to compute formula for the restricted partition function. The ingredients are just rational expressions, just fractions, and then this fractional part function, which is sort of the counterpart to the floor function. I want to spend just 1 minute on what this function qualitatively looks like. So what I see here, if I think about this as a function in n, what I see here is a linear term. And over here I see something that is a periodic function in n. So if you graph this, as we see in this picture, for the case a equals 4 and b equals 7, you see almost a linear function. It's a degree 1 polynomial, but there is noise, and this noise comes in the quote-unquote constant term of this polynomial. The constant term is a periodic function in n, and the periodicity comes from this fractional part function. So you can think about this for a moment, but the fact that we have a denominator a over here means that this first term is a periodic function in n with period a, and the second term has period b. And that's why in this graph you look at something that looks almost like a line, but it gets distorted a little bit by these periodic functions. And we call this a quasi-polynomial. So a quasi-polynomial is a function that looks like a polynomial, except that the coefficients are periodic functions in the variable. So in this case, n. We will see lots of quasi-polynomials in the book and in these videos. Okay, now let me just say a few remarks about the Frobenius problem. This is sort of the motivation for chapter 1, for why we look at the restricted partition function. So the Frobenius problem in terms of the restricted partition function says the following. So you want to find the maximal integer n for which the restricted partition function is 0. So that means we cannot write n as a linear combination of a and b, but afterwards so maybe let's write this as n plus j, the restricted partition function is positive. So this is for any j positive. So it's the last integer 0 of this restricted partition function. And so this is a famous problem. In the book we give lots of history about this problem. It's essentially open if you replace the set AB by a larger set, but there's lots of research being done, and it's an interesting sort of research area by itself. So what we're doing in the book is maybe I should give you the notation over here. So this maximal n is called the Frobenius number. And we typically denote this by g of AB. With the knowledge that we have so far about this restricted partition function, we can prove that the Frobenius number with these two parameters is a times b minus a minus b. And in fact, we can prove more things sort of related to the Frobenius problem. But what I wanted to point out is an exercise in chapter 1, so it's on the bottom of this page. It's another approach that's not in the body of the book, but it's an approach that I like very much. It's a different kind of generating function. So what you do here is you look at the set of all possible numbers that do have a representation in terms of a linear combination of a and b with non-negative integer coefficients. And now I'm not computing a generating function that keeps track of how many ways are there to write an integer in terms of the restricted partition function, but I'm just keeping track of whether or not an integer is in this set or not. So think of this generating function down here as a generating function with coefficients 0 or 1, and the coefficient is 1 precisely if k is in the set equal r. And what I'm inviting you to do is prove that this generating function is of this form, is a rational generating function, 1 minus z to the ab divided by 1 minus z to the a times 1 minus z to the b. And what's kind of nice about this is I claim in this rational function is a lot of the information about the Frobenius problem and other things. So for example, I claim we can see where this Frobenius number pops out in this generating function by saying, okay, what's the generating function? So I'm assuming now that you've done this exercise, but what's the generating functions for the integers that are not in R? So what should I do here? Well, what I can do is I can sum over all non-negative integers first, and then subtract the generating functions for the integers in R. Correct? And so this is a rational function because the first thing is a geometric series, and the second thing is what you're invited to compute in this exercise. But let's think about this for a moment. So what does this generating function look like? So as we explain in the book, and as I hope is understandable, as there is only a finite number of integers that are not in R. So here I'm again assuming that a and b are relatively prime. So what does that mean? So that means that this rational function over here is really a polynomial. Okay. So it's a generating function with finitely many terms. That's by definition a polynomial, and the degree of this polynomial is the Frobenius number. It's this number that we call g of ab. Let me finish by talking a little bit about geometry, and this is what we'll be doing for most of these videos and for most of the material in the book. So if I think about this restricted partition function again, so here you see it, what I see here is a line, is a definition of a line, in R2, and maybe I'll use variables x and y, so it's a line defined by the equation ax plus by equals n. So now I'm thinking about a, b, and n as fixed. And you can see in this picture, we're giving you several instances of this line. I guess I'm fixing a and b here, again 4 and 7, and I'm changing n. And so really what I'm interested in when I go and look at this restricted partition function is I'm looking at integer points on this line, and again this picture suggests that. And I wanted to show you this picture in part because it gives you an idea of why the Frobenius problem is a hard problem, in particular if you have more than 2 parameters. If you think about a line like this, and a and b are relatively prime, then I claim, and you can think about why this is, if I'm just interested in integer solutions, if I say x and y are integers, then this is an easy problem. So I claim you will always find integer solutions. This is a number theory problem, essentially. Yeah. So what makes a Frobenius problem hard is this condition over here, that I want my solutions that I'm up here calling k and l. In the geometry, I would call it x and y. I want these to be non-negative. And so what makes the Frobenius problem hard is if we now say, okay, x and y are non-negative, then really what we're looking is not a line, but we're looking at a line segment. And this is a one-dimensional example of a polytope. And so really what we're looking at is integer points in a polytope, not on a line. And this is what makes the Frobenius problem hard. And this is what makes our life fun. And that's one reason why we study this problem of counting or enumerating integer points in polytopes.